Right now, about 30% of single-family homes on Oahu have rooftop PV or have been approved to install a system, and those numbers keep growing. As we continue to lead the nation in solar energy, our engineers are pioneering new solutions to the technical challenges of integrating higher levels of rooftop PV.
As PV started to grow on our system, the distribution planning department wanted to make sure that the distribution system could handle the amount of power that the PV would be producing. Traditionally, the grid was designed for one-way flow of electricity, and now with PV pushing power back towards the transmission system, we wanted to make sure everything was technically sound. One of the studies we conducted demonstrated that this phenomenon called load rejection overvoltage would be the most limiting factor to high penetration PV. To solve that issue, we partnered with SolarCity and NREL to conduct some testing on new modern inverters to analyze their behavior for load rejection overvoltage.
Working at the National Renewable Energy Laboratory in Colorado, teams of engineers from Hawaiian Electric and national PV companies studied the performance of inverters, a critical piece in the interconnection between a PV system and the electric grid.
The testing we conducted at NREL took commonly used inverters in Hawaii into the laboratory, where we were able to hook up an oscilloscope to record the voltage waveforms. We were able to simulate load rejection scenarios, which means we isolated the inverter from the grid and recorded the voltage spikes that an inverter could create. And from there, we were able to analyze those voltage spikes to ensure that the magnitude and duration of those spikes do not cause harm to customer utility equipment.
The study provided valuable performance data used to identify new safety and performance standards for inverters that will help improve integration of PV into the grid.
So now that we've addressed load rejection overvoltage, there are other technical issues that can arise as penetration increases on our distribution system. So to address those issues, we're looking at a different interconnection procedure called hosting capacity, where we analyze all of our distribution feeders or circuits to determine the maximum amount of PV that can be interconnected without major upgrades to the distribution system. I think with our hosting capacity analysis, we now have the tools in place to be able to continue to meet PV growth and ultimately meet our company's goals of tripling rooftop solar and possibly beyond that.
To increase the amount of PV that can be safely interconnected, customers will need to set their PV inverters to meet these new standards. As an initial step, this enabled us to increase the safety and reliability threshold on distribution circuits to 250% of daytime minimum load. But as we continue to hit new records in PV installations, other reliability issues can arise. So we are gathering information on how these laboratory results work in the real world.
I think the most rewarding part of this process was that our team was able to work together, do some research, and gain a bunch of knowledge on high rooftop PV penetration. It was a great opportunity for our team to be able to collectively put our brains together and come up with technical solutions to integrate more PV onto our system.